Okay, and let me go to the right class, to the right lecture, just this one. All right, okay. And so a little bit of recap. So I started yesterday trying to persuade you that most phenomena in finance or economics are multivariate in nature. So they imply many variables, many time series jointly, contemporaneously. And so far, we have spent all of our time analyzing the properties of some YT, which is one time series. Now we switch to analyzing the properties of some vector YT, bold-faced, which collects many different time series jointly modeled. And the number of time series is equal to capital N. So this is the size of the vector that we are going to model. And I try to tell you what is the logic of using vector autoregressions. And then I said, before introducing formally what is a vector autoregression, there are a few concepts, a few definitions that we have encountered already that need to be adjusted, redefined if you want, because they need to apply now to vector time series, not just to one time series. And the first instance of that was weak stationarity, which means the same thing that you saw in the past, but there is an adjustment to be applied, which is now the first two moments, the mean, the variances, and the covariances. They need to exist and not depend on time, but the point is that such objects, they become more complicated because the mean is not a number, is a vector. The variance is not a number, is a matrix. It's called the covariance matrix. And finally, what used to be autocovariances, gamma h, it was a function of h. Now they become matrices because not only you have the autocovariances as we defined them in the past, so a one time series with its past and its future, you also have cross serial covariances. These are kind of autocovariances involving, however, two different time series, like the covariance y1t with y2t minus h. So you are lagging the second variable, and the second variable is actually different from the first variable. And I don't know where I stopped precisely, but we were in the middle, I think, of one example, which is about interest rates. These are short interest rates, so it's 1 month treasury yields and 10-year interest rates, so 10-year treasury yields for the US. And these are, I think, monthly data between 1990 and 2016, as you can see. Probably I told you that it's an important time series. Actually, it's an important vector of two time series, because asset managers look at this data when they're thinking about the predictive power of the slope of the yield curve. So there are many analysts convinced that if you look at the slope of the yield curve, you can get indications for the probability of recessions and expansions in the quarters following a point in time, the quarter following today. Right, so the point of this example is to contrast what happens at the bottom of this slide and what happens in the following slide. At the bottom of this slide, you have the classical summary statistics, mean, standard deviation, skewness, kurtosis, mean, and max. And you also have the correlation matrix. So if you put together the information which is inside the standard deviations, so this column that you see here, 2.51 and 1.89, together with the correlation, 0.87 that you see at the bottom, you have a way to define either the correlation matrix, rho h hats that you have in the slide, or to define the covariance matrix, which is gamma 0 hat that you saw in the previous definition. But in the case of two time series, so when you're looking at a vector process, this is not the end of the story, because there is additional information that you see. Time out, there is a noise of people working outside. Let me close the window, sorry. I'm back. There is additional information, and that's the one that you see in this slide. So from far away, it looks like autocorrelation functions. In fact, these are two autocorrelation functions. Do not be confused if you compare to the previous pictures that you saw. This is not the usual pair of autocorrelation function and partial autocorrelation function. These are two autocorrelation functions, okay? And the one on the left is between 1 month interest rates and the lag value, see this minus h here, the lag value of 10-year interest rates. So it is the correlation between today's short-term rate and the past of the long-term rates, where the past goes between 0 months, so that's this bin here, and 24 months. So there is a total of 25 values. In this case, to talk about h equal to 0 makes sense, because if I measure the covariation between 1 month interest rates and 10-year interest rates, I get this simultaneous correlation between them, which is equal to 0.87 essentially. And this 0.87 must match, as it does, the 0.87 that you see at the bottom of the previous slide. So they are the same quantity, and therefore they come with the same number. But the rest is a autocorrelation, but it's a weird one, because it's not the auto between one series and its past. It's a sort of cross auto between one series, the short-term interest rates, and the past of another series, which is the long-term interest rates. And the structure of the picture is the usual one. So these bins are the values of these cross correlations. And in principle, you also have 95% confidence intervals, but you just see the lower bound of the confidence interval. The upper bound is not visible because these bins, they are structurally above the upper bound, so they are highly statistically significant and positive. The shape of the bins should remind you of the typical behavior of a random walk, okay? But we'll talk about that when the time comes. Now, the second panel is about the cross correlations between short-term interest rates, 1 month yield, and the future 10-year yield. So in the leftmost panel, you are basically computing cross correlations between current short-term rates and past long-term rates. In the second panel, you're doing the opposite. You're computing the correlation between, if you want, current long-term rates and past short-term rates, in the sense that now the lag is implicitly applied to the short-term rates, if you think about it. Now, I know the fact that you have a cross-serial correlation between the level of the series and the plus h of another series is not the clearest thing you can think about. But that's the choice that people at VUs have done, so that's the way you will see the output presented. The information is the same as a classical autocorrelation. Same comment as before. The two pictures, they are similar, but they are not identical. So the numbers that are represented in the picture, you can see them in the rightmost columns, lag and lead. And even though the numbers are the same, are not the same, they are obviously very similar. Okay, so the two things, they behave in quite a symmetric way. The only two numbers which are supposed to be the same, they have to, it's the numbers in correspondence to h equal to 0. So these two guys, they are by construction the same. And the reason is that, as you know, correlations and covariances, they are symmetric operator when they're applied to contemporaneous values. So these are the classical correlations, covariances that you're used to. But all the other numbers, you can look at them, they are slightly different, and that's okay. So that's the nature of it. So these two columns of numbers and the corresponding plots, they are ways to visualize gamma h. So the matrix of the cross covariances between the two series which are in our vector, which is short-term rates and long-term rates. Now, how do we use these autocorrelations and these cross serial correlations? In the usual way, knowing that if a series has some memory, but the series is stationary, the memory must fade away more or less quickly. And so all these cross correlations, as well as the autocorrelations, as we have seen in the past, they must decay to 0. Now, in this case, it's not in the slide, but let me add a comment. These correlations, they seem to be decaying towards zero geometrically, right, but very slowly. You start out at 0.87, and after 24 legs, you're still at 0.80. And the suspicion is that you're looking at the typical behavior of a cross correlation coming from a random walk. In this case, it will be a vector of random walks, which is a strange process that we will comment about in the future. And but I mean, this is just a suggestion. There is no formal way so far to test what I just said. Okay. So this was an extension of weak stationarity to the vector case. Natural question is, what about strict stationarity? The definition is identical, but now you're looking not only at the joint distribution of time series over time, so each y in a given time is a different random variable, and the strict stationarity implies that the joint PDF of such sequences of random variables are constant over time. Now you're talking about the joint multivariate PDF over time, meaning that the y's, as you know, they are not just one time series, they're just vectors of time series. And vector of time series, they are not characterized by one PDF, one marginal PDF, they are characterized by a multivariate n-dimensional PDF, MS. Okay? So, especially in this case, all tricks available to avoid thinking about strict stationarity, they are useful. And what is the trick that we love the most is appealing to linearity. So anytime the VAR model can be established to be linear, you know the under linearity, strict and weak stationarity, they collapse to be the same, and therefore we will analyze only weak stationarity as we got used to do, in fact, in the case of ARMA models. Okay. Another issue that is brought up quite naturally by the picture that I just showed you is why is the picture, I mean this picture here, this one, not reporting Q-tests, Q p-values, Lune-Box p-values? Is it possible to report kind of Lune-Box p-values for these objects? It is. EViews doesn't do it, so that's one of the few, say, limitations that I can easily detect of EViews, but there are extensions of the Lune-Box test to the multivariate case, and I'm just talking about one of them here in the slide, just to know that in principle, it would be possible to actually have something like the Q statistics and the p-values that you got used in lecture number 3. So if you want to test that all the correlation matrices, to be precise, the cross correlation matrices, row 1, row 2, ... row m, so you consider m of them. So that's so far the same as what we said in the past for the Lune-Box test, against the null hypothesis that at least some of these cross-correlation matrices is different from 0, so it's not a matrix of zeros. The Q statistic can be adjusted to be the mess, it is a mess, that you see here. Anyway, we don't memorize it. Some software packages, they do carry these statistics, like State, I think, has it. And when you find it, it's called the Hosking test or the multivariate Lune-Box test. Once you do the calculation of the statistic, you can show that also this guy is distributed according to a chi-square, where the number of degrees of freedom is not just m, as it used to be in lecture 3. It is now the square of n times m, so it has a much higher number of degrees of freedom, but otherwise it works in the same way. I just noticed that there is a sentence which is not closed. The null hypothesis corresponds to, and then there is nothing. Let me see if it appears in the next slide. No, by mistake it was erased. What I meant to do, let me actually show you, I will fix it later, is to copy after this last bullet point that is visible now, the same thing that you find here. Okay, so this is to be copied there. Then I will do it. Actually, I can even You can even draw that. So this goes here. And I wanted just to emphasize once more with you that when you are applying this test, the null hypothesis is not that some row, in this case, some matrix of cross correlations is a matrix of zeros. All of them, they have to be zero, which is quite a restrictive hypothesis. When the null hypothesis cannot be rejected, however, you are facing a multivariate white noise, which is the natural generalization to the case of n variables of the classical, simple, univariate white noise. So what is a multivariate white noise? Well, it's not one single z, it is a vector of z's now, okay? So it is a vector in which all the elements, so all the time series which appear in the vectors, they are themselves white noise, and on top of that, not only each of the z has no memory for its past and no predictive power for its future, but each of the z's has no memory for the past of other z's, of other white noise in the vector, and it has no predictive power for none of the z's, none of the variables which belong to the multivariate white noise vector. So it's a complete lack of memory that goes not only within a variable looking at the past and the future, but it also goes across each possible pair of variables. It's absolute absence of any kind of memory. There will be situations in which you will use the vector z, and the assumptions that will be made to make the VAR model operational will be the multivariate white noise assumption. So that's why I wanted to have the definition. So essentially, you can read the definition. It looks like the old definition of white noise that we gave already. The only real novelty that I want to emphasize is that now not only all the autocorrelations have to be zero, but also all the cross-serial correlations inside the matrix gamma H, they have to be zero for all levels of H. So this is a generalization of the white noise concept. Okay, so time to talk about VARs now. So this was just introduction, motivation, and a few concepts that I will freely use from now on. So I will talk about gamma H, I will talk about multivariate white noise without the need to define it every time because we did that already. So what is a VAR? VAR, you can pronounce it the way you want, provided that you know you're not talking about risk management. It's basically a system of regressions in which all the n variables, the n time series that you care for, are contemporaneously endogenous, meaning that each of the time series depends on its own legs, as well as the legs of all the other variables inside the VAR. So each of them. So it's like, you will see a few examples soon in the next few slides, but it's like a bunch of regressions. But when you look at them closely, they are a mix between regressions and auto-regressions, because the variables on the left-hand side is regressed, first of all, against its own legs. So that is autoregressive, but it is also regressed against the legs of all the other variables that you have in the model. So that is kind of mixed between autoregressive and a classical regression, econometrics one style. But everything is regressed on everything. And I told you already what is the logic is when you have a bunch of variables that you know you care for on your table, on your desk, like interest rates. So you want to operate on interest rates, but you cannot pick which variables go on the left, which variables go on the right. And so what do? You put everything on the left, everything on the right in all possible combinations. And the result is your VAR model of order P. Now, what is the advantage? Well, you're really flexible. If the data have anything to tell you about the way they behave, any structure, any memory that is present in the data, they will be able to express it. What is the cost? What is the disadvantage? Well, you are creating many regressions with many things on the right-hand side. Each of the variables on the right-hand side will carry a coefficient, and therefore, very easily, a VAR model is a model very rich in parameters. So either you work with a low number of degrees of freedom, what we will say soon is a low saturation ratio, or you have to have lots of data to effectively estimate and use the VAR models in forecasting. Okay, so you see already the problem. In finance, we have little problems using them because usually we enjoy the chance to get very long time series, so lots of data, daily data, for instance. But if you try to use them in macroeconomics, then you have to be parsimonious because otherwise you build super big models that do not forecast very well. So let me look at the model formally. A vector autoregressive model of order P. In short, we will write var P. So it's like a vector generalization of the AR model. It's a process that can be written in the way that you see. So I'm not going to read it, but it's basically just a constant called A naught, is a vector of constants, plus the sum of matrices Aj that pre-multiply legs of the vector Yt. So Yt minus J, plus a vector of shocks, and the shocks, they're called U. Notice that the matrices Aj, they have to be n by n matrices, because if you take an n by n matrix Aj and you multiply by a vector Yt minus J, which is n by 1, n by n times n by 1 gives you n by 1, which is the right size, because the vector on the left-hand side, Yt, is of dimension n by 1. Okay, the UT, they are supposed to be white noise disturbances, or in brief, using the definition that I just gave you, multivariate white noise disturbances. Now, these serially uncorrelated white noise disturbances is just a long way to define a multivariate white noise. So if you write multivariate white noise, that's perfect. So the coefficients are A0 and the matrices Aj, fine. And the randomness of the y's, all of them, so the ones on the left of the equality and the ones on the right of the equality, comes from UT, from these shocks, these news. Now, obviously, if you look at that from far away, you understand that you're just looking at autoregressive model in which instead of phi naught number, you have a vector A naught, and instead of the phi j's, the coefficients that were numbers, parameters, you have matrices of parameters or coefficients, which are called Aj, but otherwise it's exactly the same thing. I mean, if you can visualize what is a vector, especially a matrix, you can immediately spot the problem in the sense that the Aj, they are n by n matrices. They, in principle, are unrestricted, so they contain n times n, so n square elements. And so if you have a model with a big N and a high P, so a big order of the VAR, you easily have lots of parameters floating around. The number of parameters in the conditional mean function is n parameters from A naught and P times n square parameters from the rest. So try to play with that. So like if n is equal to 10 and P is equal to 2, you're talking about 10 plus 2 times 100, so 210 parameters to be estimated with 10 regressions, 10 time series. So 210 parameters is supposed to be pretty scary to you. Okay, so just to visualize one, because otherwise, you know, the first time you see these objects and you come just from regressions, it may be a bit scary. So here is a case in which is a simple case, I know, but you have n equal to 2, you have p equal to 1, and that's it. And it's a finance example in which you are supposed to think that you're modeling the process followed by 2 returns onto assets, portfolios, 1 and 2, so R1 and R2. So R1 depends on a constant, and it depends on legs of itself and legs of R2. And R2 depends on a constant plus legs of itself and legs of R1. So everything depends on everything when on the right-hand side you have the legs of everything. Now, these is supposed to sound familiar in the sense that the coefficients are called phi, as before. But as you can see, the phi coefficients now, they get 2 pedices. So they have a pedix. The first pedix indicates which row are we talking about, so which variable are we modeling. And the second pedix refers to which variable is explaining the variable on the left-hand side. So for instance, phi 1, 1 means that this is the coefficient in the first equation when the first variable, lagged, is used to forecast the first variable, so phi11. Now, obviously, it's quite natural to collect phi11, phi12, phi21, and phi22 in a matrix, which will be a 2 by 2 matrix that easily we will call the phi matrix. So you just find a case, say, of the general model that you see above. Another thing to think about is that because U1 and U2, they form a vector of shocks of random variables. When you have a vector of random variables, you do not only care for their variances, so the variance of U1 and the variance of U2 called sigma square 1 and sigma square 2, but you also care for their covariance. So there is one additional parameter that becomes relevant, called sigma 1, 2, and that one is the contemporaneous, simultaneous covariance between the random shocks. Okay, so let's see, I told you everything here. All right, now VAR models, they are of two kinds, restricted or unrestricted models. And you talk about an unrestricted model when all the parameters that you see on the right-hand side of the model, so the A0 parameters, let me see if I can write, yes, and the AJ parameters, these are matrices of parameters, they do not have to contain zeros. So they contain coefficients, they contain parameters that we will have to estimate on the basis of the data. Okay? And then in a moment, I will talk about the methods of estimation. You talk about a restricted model when some of the elements of either A0 or the matrices of coefficients AJ, they have zeros. So there are parameters that we know ex ante to be equal to 0. Now, more generally, when some of the parameters inside A0 or the AJs can be set to be some number, so some number that you know before, you do not have to estimate it, but you somehow know what the number is, then you talk about a restricted vector autoregression. Like, just to give an example, so think about the case at the bottom of this slide. If for some reason I knew that this guy, phi12, is not there, I set it equal to 0, or I set it equal to some number, say 2, for some reason that I don't want to know, so I don't know where it comes from. But this VAR, as simple as it is, becomes a restricted VAR. Now, is restrictions restriction or restricting good or bad? On the one hand, it's good, because the more restrictions you have, it means that the more you know ex ante before looking at the data about the phenomenon. So you don't need the data to estimate those coefficients because you know ex ante that they're 0 or they are some numbers, whatever they are. So it's good. In fact, I told you already that one of the issues with the VARs is that they are very big models with lots of parameters. So the more parameters you can kill in advance without estimating them, the better you are. However, there is a problem. When you impose restrictions on a VAR, the method of estimation changes. The optimal method of estimation changes, in the sense that while unrestricted VARs, they can be estimated using the techniques that you know from Econometrics 1, i.e., you estimate each equation, each regression separately from the others by OLS. So you know already everything that is to be known. When the VAR contains restrictions, then you cannot use OLS equation by equation. If you use OLS, you will be inefficient. You're losing information. You're not minimizing the standard errors. There are several ways to say it, but the point is that the method of estimation that you should be using in the presence of restrictions is, guess what? Maximum likelihood. Now, maximum likelihood in the case of VARs actually is declined. It manifests itself in the form of generalized least squares that I don't know if you covered in Econometrics 1 or not, but it's a kind of a least squares in which, however, you have to weight the data, the observations, by the inverse of their variances and covariances, practically defined, okay? Now, I will talk a bit about that in the future, but the point is you cannot simply use OLS and estimate the model equation by equation, you have to apply a maximum likelihood to the system of equations. And in principle, it's considerably harder. Now, in 2021, we don't care, in the sense that anyway, machines do the estimation for us. They will get a bit slower, so they will take a few minutes instead of taking seconds at best, at worst, I would say. But this has become basically transparent to us. There are software and codes that actually decide that for you. So basically, if they can apply OLS, they do so, because OLS is mathematically is very convenient and fast. But in the moment in which there are restrictions or some coefficients set to pre-specified values, they switch automatically to maximum likelihood. Also, what if you always use maximum likelihood? You don't care for OLS. You want to basically forget about OLS? No problem. When OLS is feasible and efficient, maximum likelihood will give the same results. It will give numerically the same estimate. So you're always using a maximum likelihood is in fact appealing because of this reason. Okay. All right. Now, the other distinction that is useful to have in the case of VAR models is a distinction between standard reduced form VARs and structural VARs. So the VAR that I showed you in the definition, let me go back, this one that you see in the middle of the slide, is a reduced form or standard form VAR. And that's the most used way to represent VARs in the case of financial applications. Okay. So why standard? Why reduced form? Because if you think about it, this way of writing the VAR prevents the variables, the time series, to interact with each other directly. I mean, what I mean is that there is an identity matrix here that multiplies YT. So the only way in which the YT can interact with each other contemporaneously in this VAR is through UT, is through the covariance matrix of UT. So if the variables inside YT, they want to move together contemporaneously, the only way they have to do that is through sigma 1, 2, the covariance of the shocks to the variables. So it is as if you have already imposed some kind of standardization, that's why it's called standard, to your VAR. And in principle, there may be a loss of information because you're forcing the YT variable to commove only through the shocks, and they cannot commove directly. So they cannot commove, say, explicitly by having a matrix in front of YT that is different from the identity matrix. So when you do not want to impose the standardization restriction, so you don't want to use a standardized or reduced form VAR, you can. And it's another kind of VAR called structural VAR. So when the contemporaneous relationships between the Y's, so the variable inside YT, do not have to go only through the UT, only through sigma 1, 2, but they can also go through contemporaneous true relationships, then you talk about a structural VAR. Now, why is that relevant? Because estimation and forecasting with reduced form VARs is easy. And in the absence of restrictions, standard reduced form VARs, they are actually handled as regressions just by doing OLS equation by equation. So the lecture could be over practically. Things become instead interesting when you have a structural VAR. So when the Y variables, they are allowed to interact with each other contemporaneously, not only through the shocks. And in this case, estimation must be done carefully because you will see what I mean between today and the next lecture. There can be issues of identification. Identification, just remember the word for the time being. Now, to be concrete, because these things are not really well explained just in abstract, I want to consider one example. And this example is an important one in the sense that we'll spend like 1 hour looking at that. And there is some algebra, which the slides kind of do, but kind is not doing it. And so in the lectures, I will comment the slides, and I will actually kind of mimic the algebra to be done. but I know that for some of you this is new, so you have a right to see what's happening. And so last year I recorded a video in which basically I do the algebra in front of your eyes step by step. Okay. Technically, I might go back to the whiteboard, but I don't know what is happening. So after the break, we'll talk about that. All right. So this one that you're seeing is a structural VAR model for two variables when p is equal to 1. So you see that there are two equations, and the variables that are in play, they are called x and z. So n is equal to 2. P is equal to 1 because if you look at the right-hand side, there is only one leg of both variables. So for instance, in the first equation, you see xt minus 1 and zt minus 1, t minus 1. So there is only one leg. So p is equal to 1. And why do I say that this one is a structural model? The reason is that, obviously, clearly, unless something happens to the coefficients b12 and b21, xt depends on zt if b12 is different from 0, and zt depends on xt, sorry, if b21 is different from 0. So the presence of contemporaneous effects, so contemporaneous dependence of x on z and z on x, which does not go through the shocks, does not go through these guys here at the end of the equations, epsilon tx and epsilon tz, makes this VAR model a structural one. And you will see why, but structural models, structural VARs, they have to be approached with care, with lots of attention, and you will see why. The shocks, because they are shocks to a structural VAR, they carry a different name. They're not called U's as before, they're called epsilons. Epsilon x and epsilon z. And because otherwise there is a problem of confusing the contemporaneous dependence between x and z that comes from b12 and b21, and the contemporaneous dependence which comes from any covariance between epsilon tx and epsilon tz. Structural errors, by definition, are standardized and normalized, we say, to be uncorrelated. In fact, the assumption that epsilon tx and epsilon tz, they have a zero correlation, contemporaneous correlation, makes them structural errors. So in a reduced form VAR, in a standard VAR, the contemporaneous correlation must go through, let me go back to the definition, the contemporaneous correlation, it must go through U, must go through the covariances inside the covariance matrix of the U's. While in a structural VAR, the contemporaneous dependence, the contemporaneous connections between pairs of variables can only go through coefficients which are part of the conditional mean specification. All the work is done by the coefficients and is not done by the epsilon. You may ask, is it possible to write down a model in which I've got the coefficients b12, b21 working? So there is a direct visible connection between the variables, but also the errors, they are correlated. In principle, yes, but this will create problems of identification because you will never be able, in a linear world, to tell apart the role played by the b12 and b21 coefficients from the role played by the covariance between epsilon tx and epsilon tz. So to solve this problem from scratch, from the beginning, there is usually an assumption that structural errors, they are not correlated. Okay, now, so I will start approaching the structural modeling, and next time I'll review and close which is the right way of doing that, so that you have a couple of chances to think about it. So the first thing I want to do is to rewrite the model in terms of vectors and matrices, which is also useful because many of you are not used maybe to work with vector and matrices. And in the matter of VARs, unfortunately, we have to, otherwise it's too messy. Okay. So first thing, I basically placed everything which is contemporaneous, everything that is indexed time t, to the left of the equality. So I can move this guy here, b12 times zt, from right to left. And basically, you're summing b1t times zt to both sides of the equation. And I can move this guy here, minus b21xt, from right to left. So same principle, same comment as before. If you do so, you can represent the left-hand side as the product between a matrix B and a vector yt, which collects xt and zt. Okay. Now notice that calling things x, y, z doesn't matter, right? But because in the definition I've called the variable yt vector, now I want to be consistent, so I collect the variables x and z inside the vector which is called yt. The matrix B has a special structure which would be useful. It is made of ones on the main diagonal, and it collects B12 and B21 off the main diagonal. And the indices, so 1, 2, and 2, 1, they are the appropriate indices when you are calling something inside the matrix. On the right-hand side, there is everything else that has been left. So there are two constants called gamma 1, 0 and gamma 2, 0. So they are collected inside the vector called gamma 0. All right. And many of you will recognize that these portion of the model, so these square essentially, can always be written as the product between a matrix with elements gamma 1, 1, gamma 1, 2, gamma 2, 1, and gamma 2, 2, and the vector, when the vector collects x t minus 1 and z t minus 1, which is what I've done here. So there is a matrix gamma 1 multiplying the leg of xt and zt, and this legged copy is a leg copy of yt, so yt minus 1. Finally, I collect the two structural shocks, epsilon tx and epsilon tz, in a vector called epsilon t. And here in the middle of the slide, you see the model written just using vectors and matrices. All right. Now, what is typical to do is the following. If I leave the model in this way, it's not a regression, right? And why do I say that? Because in the regression, think about it, you have to have yt alone on the left-hand side and all the other stuff explaining yt. If there is something in front of yt, or there are two variables on the left-hand side and many variables on the right-hand side, that thing is weird, it's not a regression. So here, if I leave the model, the structural VAR, the way I see that, there is a problem. I would like to see that as a regression, maybe apply OLS because it is a regression, but I can't. And the problem is that the presence of this B matrix complicates matters. Sorry, the presence of this B matrix is problematic. All right, can you get rid of a matrix in one vector matrix equation? Yes, you can, if the matrix is square and you can find the inverse of the matrix. So let's suppose that things go well in this case, and the fact that you have ones on the main diagonal of the B matrix, these guys here, actually makes this matrix always invertible in reality. So yes, you can find the inverse of B. And how do you get rid of a matrix? Well, you pre-multiply the left-hand side and the right-hand side by the inverse of B so that you can get rid of B on the left-hand side. The bottom of the slide does that. You multiply both sides by the inverse of B. This is possible basically if the product between B12 and B21 is different from 1. So the only case in which you have issues is when B12 and B21, they come in, say, inversely proportional fashion, because one is the inverse of the other. But let's suppose that this does not happen. So it's a restriction that we have to keep in mind for later. Right? So it will pop up again. And otherwise, you pre-multiply everything by the inverse of B, so you lose B here. So this guy dies, so it goes away. As you can see, there is nothing now. And everything else gets multiplied by the inverse of B. So you got inverse of B times gamma 0. Now, the inverse of B is the inverse of a matrix. The inverse of a matrix is a matrix. Matrix times vector gives you a vector. And so this product, B inverse gamma 0, is a vector, and we call this vector A naught. Then you have the inverse of B times gamma 1. Now, B is a matrix, the inverse is a matrix. Matrix times matrix is a matrix if the dimensions are right, and they are, because everything is n by n here. So matrix times matrix is a new matrix, and we call this matrix A1. And finally, you have inverse B times epsilon t is a matrix times vector, and it gives a vector. And this vector is random. And the reason is that epsilon t is made of random variables. And if you just multiply, sum, and combine random variables, in general, you have new random variables. And these new random variables, they're called u1 and u2, and they're collected in the vector ut. But what has happened, by doing that is that I started from a structural VAR, and by applying a transformation which goes through the inversion of the matrix, I was able to get the structural VAR into a reduced form VAR. And the reduced form VAR is characterized by parameters A0 and the matrix A1. And there is a new set of shocks, and the shocks are called UT. Now, what is happening is really that I have moved one complication. What was the complication? The complication is that if I don't do the math that you just saw, as I was telling you, this equation, this VAR here, the structural VAR that you see here, is not a set of regressions, is not a system of regressions. And I would like to work with a system of regressions. And so the fact that originally structural VAR cannot be seen as a system of regressions is a complication. Now, by multiplying both sides by the inverse of B, pre-multiplying by the inverse of B, apparently I got rid of the complication, because now I got this at the very bottom of the slide, the reduced form VAR, which now is a system of regressions. And you could be all happy. All right, we solved the problem. The problem has gone from the presence of B to the fact that we messed up the errors, in the sense that originally the structural shocks, epsilon Tx and epsilon Tz, they were pure white noise shocks, in the sense that they were white noise individually, and they were not even contemporaneously correlated, because we said that they're structural, because the covariance between epsilon Tx and epsilon Tz is equal to 0. But because of our pre-multiplying them by the inverse of B now, we have created two new shocks called epsilon Tx called the UTX and UTZ, these two guys, which now are in general correlated. And I will stop now because I want to open eViews and phase towards the labs. But essentially, this algebra on top of the slides makes two things. First, it shows what is the inverse of the matrix B. And you have your rules of inversion of matrices. You may want to review them. They were in the prep course if you go back. But it's basically just the adjunct matrix. This thing is called the adjunct matrix. It is basically obtained by transposing the matrix and computing something called the principal minors. But please go and review them in the prep course if you forgot, or in this case, anyway, you do not have to memorize, right? Because the algebra will not be required, but trust me, that's what it is. And when you're inverting a matrix, remember that you have to divide by the determinant of the matrix. The determinant of B is given by 1 minus B12 times B21, and that's why B12 times B21 cannot be equal to 1, because otherwise, when I invert the matrix, it blows up, because you would have 1 divided by 0, which mathematically you cannot have. Now, if you take the inverse of B and you do the algebra of pre-multiplying by the structural shocks epsilon Tx and epsilon Tz, you can check. And if you don't believe me, I will post the algebra soon over the weekend. If you want to do the algebra, that the result is given by these two things, these two expressions. Now, the problem, I'm about to stop, so I will stop here, is that these new shocks, UTX and UTZ, which are the reduced form shocks, they are no longer basically displaying good properties. They are still white noise, but they are correlated with each other. And this creates a potential issue that we will analyze on the next episode. Okay, so I will stop here with the lecture, and I will switch to sharing my screen, and I will open eViews and show you a few things. I will open first Blackboard and then eViews and show you a few things. So share my screen. Okay, now you got funny, no? Okay, funny echo effect. And the first thing I want to do is to show you Blackboard. That's the attendance page. So here on the left, guys, let me check that before I waste my time. are you seeing my screen now? Are you seeing my Blackboard? All right, thank you. So if something goes wrong, please immediately tell me. All right, so under my contents, I have created one additional tab, which is optional labs. And if you go inside optional labs, there are already 2 items. And today I'm going to basically move myself between the 2 of them. And one is just an introduction to eViews. It's very slow, step by step, basically also teaching you how to download the free version of eViews, by the way. How do you upload the data? How do you plot the data? How do you prepare a table with summary statistics? How do you format tables and figures? Really teaching how to use the software. It's a very intuitive software. You're not very many steps away from Excel, honestly, but still, it's fair that you guys also learn the software in some depth because you can use it in the future. And there is a set of slides related to that, right? The very first line, so you can read them, you can download and take a look at them as well, besides listening to the recording. The recording is by Manuela Pedio, by the way, who's our head TA, the tutor. And there is also a second lab, which is part of what I will do today, in which you have applications of ARMA modeling to cryptocurrency prices and especially returns. And there is one example with Ethereum, which I will also use today. And there is one example based on Bitcoin data, for which we have some results. And in all cases, you can download the data. You can download the slides that are commented by Manuela in the recordings. And in some cases, not in this case, but in some cases, you also have the eViews files. Right? So what are we supposed to do here? Well, if you plan to be active, because you work in a group, remember, but if you plan to be active in your homeworks, then I would do this. Or if you plan to do empirical work in your future, using simple tools, eViews is very simple because it's just clicking and analyzing essentially, then it's a good idea to exploit the opportunity offered. If you are not planning to work on the homework, then I would not do much, but I could still open the slides because they show lots of outputs. And getting a sense for a feeling for what the outputs mean and understanding what the comments on the outputs in the slides are and why they are what they are may help you in preparing the exam. But I would pay much less attention to this. Okay, I think I told you everything. Yes. All right, so let's go to eViews now. So mine is the pro version of eViews, which is provided by the university. It's the 11. I think that if you follow the instructions and if you have Windows, they will give you 11.5 possibly, I'm not sure. The free version that you can download seems to be the 11.5. So question is, what is the difference between 11 and 11.5? There are some differences for very fancy stuff. 11.5 is better. But for the things that we have to do together, there is basically no difference. So even eViews 10 probably is okay, or eViews 9. But I just don't know, but I do not expect that we will be using very fancy functions or new types of analysis that they have introduced. Okay, so the first thing you want to do is to create a Word file. And you do that by clicking here. So let's create a new one. And then you're given basically 2 options. And this is the first encounter with eViews. For some of you, I don't know the fraction of you saw eViews, but it's, I mean, it's much simpler than R, than Python. So we're not talking a programming language, although you can program in eViews. Very few people do because it's not entirely flexible. So the real restriction of eViews is that it does not allow very easily manipulation of vectors, matrices, of the mathematical objects that you get. Instead, the typical software, programming software that you are taught, so R to some extent, but especially MATLAB and Python, or C or Fortran, these type of things, they are languages in which you have to do direct manipulation of the objects, vectors and matrices. Now, is that an advantage? Yes, it gives you entire flexibility, full flexibility on the things you can do. What is the cost? Well, you have to learn really how to program, right? You cannot pretend. And second, even trivial things, they may cost you several lines of coding unless you have already your procedures. eViews is sort of a high-level language in the sense that it's little object manipulation, and there are rows of commands which already spit out very rich output that you can retrieve and use for other things. It's very similar, if you have ever used it, to Stata. So Stata and eViews are kind of close, although Stata got a bit better over the years in object manipulation, and eViews stayed what it was. Right. So if you listen to Manuela in the introduction to eViews, she also shows you stuff about programming and what the options are. Right. So that's the first encounter, but basically you already understand what you were talking about here. So there are lots of drop-down menus in which you choose things here and here. And there are occasionally some spaces in which you're supposed to write things, but it's kind of limited, right? So little keyboard, lots of choosing and clicking. Okay, so the basic idea is that you can import unstructured data, regular frequency data, like in time series analysis, and you can also import panel data for those of you who know what panel data are. But it's a kind of econometrics, which is very useful, but it's not time series. So we don't worry about it. So in our case, we care for regular frequency data because we are in a time series course, and we are about to import daily data. So these are the frequencies which are available in eViews, and as you can see, there are many kinds of frequencies. Also weird ones like 10-day data. I never use them. There must be some place in which they make sense. So in our case, we are about to use daily data 7 days a week. And the reason is that I will import and play a little bit with cryptocurrency returns, cryptocurrency data. And cryptocurrencies, in case you don't know that, they have one feature: they are traded always, every day. So the market is an electronic market, is entirely over-the-counter, kind of unregulated market. In fact, it's a private market. And as such, there are no limits to where or when you can trade. Actually, one of the problems with the cryptocurrencies is that they are traded on a number of competing platforms, and it's kind of chaotic, the situation right now. There are some bigger platforms, smaller platforms, but they are always going and always open, so 7 days a week. Now, we need to specify the start date and the end date, and that's the most important peculiarity that eViews has. It's a US software, and even though it's distributed around the world, they always kept the US way to specify dates, in which you put first the month and then the day. So first the month, 2 digits, and then the day. Okay, so remember that, because sometimes people get stuck. So they open, and after 5 seconds, they're there swearing and stuck. And sometimes you can create data sets in which the starting date or the end date, they are completely wrong, because if you flip around numbers, you can get things which are not the ones that you want. Now, in my case, I already forgot the start date and the end date, but it's also a good excuse for me to go to the lab. It's called Lab 2, and open the data, which are these. It's an Excel file. Maybe it opens. Wow. That just tells you about my computer, not about Excel, in fact. But, sometimes it happens. All right, here we go. And as you can see, there are 2 worksheets, one for Bitcoin and one for Ethereum. All right. And the data for Ethereum, they start in the 10th of August of 2015. And as you can see, the dates are already written in the way that eViews will like, just to avoid misunderstandings. So 8/10/2015. And the last date available for Ethereum is, I think that the data on Ethereum, they entirely fit your eViews if you're using the free downloaded version from the eViews website. So it should fit the data. And Bitcoin is a bit a longer time series because we extended it to 2020. So if you experience problems, you just have to cut it, okay? No drama. So 18th of April, 2020. Okay. So it is April 18th, 2020. Right. At this point, it has created a worksheet. A worksheet is an object which is like looking at Excel. The only thing is that in Excel, you always have a visual of your series. They're just written one on the side of the other, column by column. In this case, instead, the series, they are contained in these little, say, boxes, these little icons. And you can look at them by clicking on them. Now, you may be surprised, so how come you just created a Word file and it already contains stuff? This will always be the case in eViews. These two icons, they contain the constant, is really the intercept. So we're really talking about phi naught, mu, or alpha of the regression. And I don't know why, but for some technical reason, they always have to have at least one parameter, and that's the one. And it contains already an empty series of residuals. So if you open, it's entirely not available. Why? Because we do not have data. We didn't do anything yet. But I mean, eViews to work needs to have at least one time series open, just to initialize things. Okay. So anytime you will open it, you will find these waiting for you. How do you import data? As I told you, we'll go kind of quickly, right? So I'm not really waiting for you to copy what I do in eViews. But if you want to do that, which is very useful, what I suggest is that you put up the recorded classes, lectures by Manuela at this stage, but then there will be also recordings done by me. And essentially you listen, you repeat the operation, so you stop, you repeat the operation, you listen, you repeat the operation, and so basically you can learn to do the same things that we did. All right, so I want to import data because as you saw, I have them in Excel. So import from file because they are in a file. It opens stuff, but the file that I want to have is inside Lab 2, and it's called Crypto Data in Excel Updated in this case. All right. Now, there are several panels that in principle you can play with by choosing to just import some observations and not others, just some columns and not others. You can actually import already applying transformations to the data that you are importing. So these sequence of operations that are offered by eViews is quite rich. But in our case, we go straight to the point. If you want to understand and know about those options that pop up at this stage, listen to the first recording by Manuela Pedio. So I do avanti. Right, my eViews speaks Italian, kind of. It's kind of hybrid, actually. I never realized that it was speaking Italian, but it must be pick up the language from the computer, but it's just forward. Now, in this case, it's basically wondering where I should take the names of the variables from. And my Excel file has names on top of the columns. And what is proposing to us is to read the names of the variables already automatically from the tops of the columns. So fine. Then it's wondering, so how am I supposed to represent the not available data? I don't think we have not available in this data set, but in case. And so that's the standard way of eViews, so nothing to worry about. And at this point, it has already kind of preloaded the data. So you saw that it thought for a moment. And this is the way in which my spreadsheet seen by eViews looks like. So there is a series of weird characters. These are dates. And then there is a price index. That's the price of Ethereum, which is a cryptocurrency. If you want to know something about Ethereum, please also listen to the second recording by Manuela, and she spent like 5 minutes talking about it. And these are the price returns by Ethereum on Ethereum, and that's the hash rate. Two words on that. The hash rate measures the speed with which new crypto coins are mined, meaning they are created. And the mining process, the creation of cryptocurrencies, is a function of the computational power that is devoted to the process of essentially coding the blockchain. Right? So I don't want to go into details because I'm not really the fintech person to explain this, but the hash rate is like the speed and the volume at which the coins are supplied. So you would expect the returns on Ethereum, the price of Ethereum, to reflect the hash rate, meaning that the more the hash rate is high, and the more the index should be actually low, because it's like the supply of Ethereum increasing. Or in general, you would expect that hash rate may carry some predictive power for the price returns on Ethereum. We'll see whether this is the case or not. So, but just to tell you that we are importing the price, we're importing the returns already calculated from the price, okay? And finally, we are importing some explanatory factor, some economic factor called the hash rate. Okay. Now, if I just click finish, it will give you a mistake, because basically, and you already have indications of the mistake about to happen in these question marks, because EViews is very prickly when it comes to reading dates, and these numbers that you see inside the column series 1, they are not really dates in that way. So the right way of doing is to do a sequential read, if I remember well, which means that everything will be read as it comes in the sequence, filling the observations between the 10th of August 2015 and until the 18th of April 2020. So I click finish. This one means, do you want me to change the EViews file in case the Excel file is changed in the future? So you can also do this type of automatic linking. Let's say no. All right, and the data got imported. Now, I do not have time. We still have 20 minutes to go, so I want to do some ARMA in front of your eyes. But if you, so series 1, so if you click on the series, you see them. Series 1 can be discarded. It's the dates in Excel. We have our own dates that we filled automatically in a sequential pattern. So I would do a delete on the dates. And it may be a good idea for us to save everything. So you just do save. It's the first time we save, so it will offer the possibility to save things around. And in my case, I will save on top of the old Ethereum, which I had already, but it's not a big deal. Okay, now let's look at the true things quickly. So let me click on, no, wrong already. Let me click on price index, and you see the prices. So it's a good idea to go up and down and check whether there are weird things happening, weird numbers, or not available, but that's not the case. And the way you plot a picture, a graph in EViews is very simple. You go under View, you do Graph, and when my computer wakes up, the Blackboard thing is actually slowing it down. All right. Then you have choices of which types of graph you can actually plot. So, I mean, if you look at the recording, there are some examples, but if you are into graphs and into presentations, that you have to look at the manual, I think. In this case, I just want the plain vanilla graph, line and symbols. And here we go with the, so let me actually make it bigger. That's the Ethereum price index. Now I know that recently went up again. We are in the middle of what some people think is a bubble for cryptocurrencies, all right, but it was already a bubble. Some of you actually are aware of that in early 2018, late 2017 actually. All right, but let me also look at the returns. the returns will not be very memorable. And you know why? Because the price is supposed to be under the efficient market hypothesis a random walk. And so it just goes up and down without any stationary point, any memory to go to. And the price returns instead, they are the typical return series that I think we have opened already a couple of times. They go up and down. There are periods in which there is visibly a lot of volatility, some possibly negative jumps, and periods in which there is little volatility, like during 2000, I would say late 2016, or like late 2019, but that's all you see. And finally, let me show you the hash rate quickly. Wow, the blackboard is really drag. Okay, that's the hash rate. I know that the hash rate that I'm showing you is different from the one that you see in the slides, in the blackboard. If you go and check it out, and the data have changed. So I checked the data. I mean, a while after the lab in 2020. So essentially 1 year ago, and I found that they were different and they changed. So I replaced them with what I believe are the right data. So these are correct now. Okay, so what I want to do with you. So first of all, teach you how do you estimate a regression by simple OLS in eViews, and what the information coming out of that are. And then I want to try and estimate a few ARMA models automatically and by hand. All right, so how do you estimate a regression? So you do quick estimate equation, and then a window pops up in which you can specify the dependent and the independent variable. And actually on top, you also have some guidance on how do you do that. Now, there are two ways. You can write an equation with coefficients, as you see here. So that's the example that eViews is giving. But there is even a simpler way, which is completely okay for our purposes, which is to write the dependent variable first. So in my case, as always, I care for explaining the price return, not the price index, because the price index should be non-stationary, and working with non-stationary variables is not a good idea. So after the dependent variable, you can actually enter the regressors. And if you want to include the constant is called C. And it's basically a placeholder for a vector of ones. So you probably know from Econometrics 1 that every time a regression model includes a constant, that's equivalent to estimating the coefficient, which is in front of simply a vector of ones. And then as explanatory variable, I think is a good idea to use the hash rate. Notice that eViews is actually also giving suggestions on the name of the variables. And because we are into predicting, let me use the lag hash rate, which means that the hash rate of today forecasts the return on Ethereum of tomorrow. Okay, that's the equation I want to estimate. Now, here in the method, you have the available estimation methods. Some of them are really a foreign language, because these are things that you never saw and you will never see in the MSc. We care for like 3 or 4 of them in general in the MSc. For us, we'll use LS, which is least squares, which is not just OLS. It could also be NLS, which means nonlinear least squares, but it will depend on the application. And it will also see me in the future using ARCH, which is a way to say maximum likelihood estimation. There are other things which are very fancy, but there is a maximum likelihood here, but it's a weird one. So it's not really something that we care for. So in my case, OLS is fine. Now here at the bottom, in principle, you can change the sample of estimation if you do not want to use the entire sample. But at this point, I have no reason. Then you click OK. And it takes about 1 second, a bit less, to estimate the regression in eViews. Now, I know that I do not sound nice, but keep in mind that in 2021, if you write a thesis, or if you show results to your boss, and you say, well, but I estimated the regression, people, they really visualize the fact what just happened in front of your eyes. The consumption of your time was about 1 second, right? So it's not a proof of effort having estimated a regression. The work of preparation of estimating a regression, downloading the data, making sure that the data makes sense, that the regression is a sensible one, and making sure that the results make sense is an effort. But estimating the regression in itself, 1 second. Okay, and this econometrics one, so we'll not spend much time, but what's happening is that the p-values of the constant is between 1 and 5%, so there is at least a positive coefficient, but the predictor variable, the hash rate, is not statistically significant. The p-value is equal to 0.89. The t-stat is in absolute value very close to 0, so there is not much. The R-square is bitterly disappointing. It's a bunch of zeros, and then finally there is a 1 appearing somewhere. And actually, I don't want to do that, but if you fish around, you will see other problems with the Durbin-Watson statistics, stuff like that. Now, one thing that I want you to notice and kind of keep in mind is the value of the information criteria. And we're talking about a minus 2.67, essentially. They're kind of all the same in this case. All right, that's a regression. What do you do with the regression? Well, first of all, it may be a good idea to actually plot the results. So there is a visualization in which you plot both the actual values, which are the orange, the fitted values, which is the green. The green is almost a flat line. That's not surprising because the coefficient of the hash rate was very small and not statistically significant, so it doesn't do much. And the blue, the plot underneath, is actually the residuals, the epsilon hats, I call them. And as you, obviously, because the green line is almost flat, is almost constant, the blue and the orange are almost the same, meaning that your model is not explaining very much of the phenomenon you care for. But there are other things you can do, like some of them, they should have been covered in econometrics 1. You can build the confidence intervals, you can build the joint confidence intervals for the coefficients, you can test hypotheses, you can apply tests for whether you have omitted variables, for whether you have included variables that should not be there, and so forth. So some of the topics that you must have discussed in econometrics 1, they correspond to things you can click here. Also, and this is something that we kind of discussed, you can do diagnostics on the residuals. Do the residuals behave in the way you expect? And I just want to show you one of them because it's an introduction to using ARMA models. So if you just do these 2 clicks, you get something that you've seen a few times in the slides and in the lectures. That's the typical plot of ACF, PACF, QStat, and p-values for the residuals of your regression. And guys, we have a problem in the sense that initially the p-values, they are not that bad. They go up and down, but they're kind of acceptable because they are above 0.1. But then they become small, and towards the end, we are below 1%, meaning the residuals from the regression that I've just estimated, they seem to contain memory. They are supposed to be white noise if you want your regression to be correctly specified, but they are not. So usually at this point, there is an indication that you have to switch away from a regression analysis into an ARMA style analysis. What does it mean to do that? Well, it means that you go back to re-estimate your model, but instead of estimating a regression, you want to estimate a ARMA model. How do you do that? So first of all, if you are into moving average processes, these are specified and estimated in a very simple way in eViews. You just specify how many moving average components do you want on the right-hand side. And so if I write MA1, it means that I want one leg of the shocks to the right of the model for the price returns. But let me add MA2, okay? And then let me skip one. So it's meaning, the meaning is that θ3, the third coefficient of the moving average process, will be set to 0. So it's like a hole. And then I have MA4. Okay, just to try one, okay? And here you see that least squares is called least squares, but then it specifies ARMA. And that's kind of sloppy of the eViews creators, because we know that when there are moving average components, the model should be estimated at maximum likelihood. And that's what it does. So let me click OK. So this is MA4 with a hole. So it's not really a trivial model. And the estimation takes 1 second. Okay. And in fact, even though the drop-down window was a bit weird, eViews is able to do the right thing. So we know that when there are moving average components, we have to estimate things by maximum likelihood, and that's what eViews does. And these are the results. eViews is very good in showing that also sigma square epsilon, as I stressed a few times in the classroom, is an estimable parameter, so it should be estimated, and it puts that inside the set of estimable parameters. Now, one critique, this way of reporting output has been there. It has been the same with no changes as far as I can see since the mid-1990s. So it has been like this for 25 years almost. And there is one thing that was never fixed. Here they write variable, and not always the things that you see here, they are variable. So the constant is not a variable. Sigma square is not a variable, right? So variable is the stuff on the right-hand side, basically, okay? It's not called variable. Right, things go kind of okay. I mean, some coefficients, they are statistically significant. MA2 is statistically significant, and some others are not. The R-square, I told you things about the R-square, has improved a bit. It went from 0.00001 to 0.035. So it's like 35 times bigger, but it remains a small R-square, obviously. Okay. Can we improve the model? Well, let me show you how do you estimate an AR1 model, or AR model in general. So you do estimates, you go back here, and you change things. Now, there are two ways to estimate autoregressive models. That way that actually corresponds to the things that we saw in the classroom is to use on the right-hand side the variable that you have on the left-hand side. So I rewrite price return, and I leg it, so -1. So let me estimate an AR2, just for the fun of it. I include 2 legs, and then I click OK. It takes 1 second again, and once more, there is a p-value, which is between 1 and 5%, so there is something statistically significant here, but the AR1 coefficient is not statistically significant. The R-square remains disappointing, but it clicked up a bit from 0035, I think, to 0037. How do you estimate ARMA model? Well, let's leave the stuff here, but let's also put MA1, MA2. You click OK, boom, it takes still the same time. And now there is magic. There is something going on here. So adding the moving average components has made everything to become statistically significant, but there is a problem. The coefficients, so see 1.24, they're kind of matched, so between the AR component and the moving average component, and they're kind of almost the same, but they have opposite sign. So 1.24 minus 1.25 and minus 0.72 and 0.76. I mean, okay. So when models behave in this way, they are trying to signal something. You have to listen to the recordings to you will see what I mean. The R-square has now gotten decent. So we're talking about an R-square of almost 3%. Right? And now let me, still 5 minutes. Let me tell you one thing. So what if instead of, so there is an asymmetry, because when I want an AR, I have to use the lag values for the Y, price return. When I want an MA, I just write MA. So what if I do this? AR1 and AR2, and then I leave the rest as it is. Before I click OK, look at the coefficients, and because I wanted to notice the changes that will happen, so I click OK again. And now the coefficients are completely different, as if I have changed drastically the variables. What's going on? In EViews, if you write not the lag values of the dependent variable, if you write instead AR something, AR1, AR2, you're estimating a model which is a model in which there are autoregressive terms in the shocks. So the autoregressive stuff is about the epsilons, is not about the value of y. So it's kind of a hybrid, if you want, between moving average and autoregressive. So don't use, unless you know what you're doing, AR in the specification of the model, even though it seems to be appealing. All right. Now, so the first thing I want to do is to look at the ACF and PACF of the data with you as we did in class. So to do that, let's estimate a simple model in which I just have a constant. So there is nothing, right? That's the model. That's a silly model. And then I want to use the residuals. And the way you do that is by using parallelogram, Q statistics. They use 36 of them. And let's think about the ACF and PACF. And well, first of all, the bins that you see are kind of small everywhere, but okay, first comment to be made. And as noticed before, there is some hesitation initially in the Q statistics, and the reason is because the second leg of the ACF is statistically significant individually, and it brings down the p-value. But then, as you can see, the Q stat goes up, and it comes down again only when you get to the 17th, the 18th, and especially the 19th leg. So 17 and 19 are really what makes for the behavior of the ACF. Now, if I show you ACF and PACF like this, there are two comments you can make. First, there is not much to be seen. So most of the bins are not statistically significant. And this series seems to be kind of close to a white noise. First. Second, well, the ACF and the PACF, they seem to be symmetric. They kind of behave in the same way, if you think about it, right? They always seem to go, with a few exceptions, in the same direction. And even the values, they are not really far apart from each other. I mean, they're not the same, I'm not saying that, but they're not far apart from each other. But there is for sure some structure, there is some memory. I mean, if there were no memory, these p-values between 0.1 and 5% that you see after legs after leg 16, 17, they could not be there. So it's not a white noise. It's not a clear-cut case of R model or moving average model. It is something hybrid, something very difficult to detect. And so you may go like, well, how do I do now? So should I try everything that is on the table? So everything that had been taught? There are a few cases that are in the recordings, but let me show you just one trick, which is, let me close the equation. Right? There is no problem in doing that. Let me go to the variable that I want to model, which is price return. So let me open it. It's a picture now. But there is one quick trick. If you go to PROC and you do automatic ARIMA forecasting, there is a procedure which allows you to use information criteria to automatically detect what is the best model. So the stuff that we did in a table in the classroom manually, by reporting numbers by hand, can actually be done automatically. So the way you do it is by, so forget about differencing because we are looking at returns. And let's go crazy here. So let's say that you can have 4 legs of the autoregressive part, 12 legs of the moving average. I would like to have more even, but it does not allow me to. And nothing else here, fine. And here you are allowed to specify what is the criterion based on which you do the model selection. So you see you have Akaike, Schwartz, Hannan, Quinn, which are the same information criteria that we spoke about. And then there is the mean square forecast error as well. But let's pick, I don't know, let's pick Akaike, for instance, right? And let's tick everything. So it will give you more output to look at. I'm about to close, guys. I know that I need to finish. If you do okay, you will see stuff happening here at the bottom. So EViews is estimating and producing results for 65 different ARMA models, so just in a sequence. And then it will be offering, in about 1 minute, indications about the winner. what is the optimal ARMA model that these series of cryptocurrency returns are needing. So you need some patience. I mean, we are estimating 65 models in about 1 minute, 1 minute and a half. So I mean, it's still impressive. Some patience. Let me comment what you see. So you also have indication about what model is being estimated, so what P and Q are. And you see that there is a log L that is running, the numbers are changing. And the reason is that, remember that with ARMA models, the estimation must be performed by maximizing the log likelihood. And what you see happening at the bottom of the screen is exactly the maximization of the log likelihood. We are at model 60. Hold on, guys, just to see what the winner is, and then I will close shop. 61. It is a bit slow compared to what your machine will be like, because I got Blackboard open, and is quite absorbing in terms of memory. 64, we're almost there. Model number 65 is about to end, and then we'll see what the winner is, maybe. All right. So now it's doing a final round of estimation, and it is done. The winner that has been detected, it's visible. Well, first of all, it is visible here. So the selected ARMA model is a 210 model. So there are 2 legs of the dependent variable and 10 legs of the moving average. The model has the structure that you see here at the bottom. Okay, this is the model that has been estimated. And if you look at the graphs, it is actually also visually comparing based on the information criterion, the Akaike criterion, that, remember, you want to minimize all the top models that have been compared and estimated in the run. All right, so let me stop the sharing, come back. So, so where are you guys? Boom, boom, boom. All right, so let me put my face. All right, so guys, if you care for the labs, there are a couple of recordings to look at in which the things that you saw with me and more, slower, they have been done for you, with also comments about cryptocurrencies if you care for the comments and the application. Take in any case a look at the outputs, because in the exam there will be some outputs not coming from the labs, but they will be outputs. So to be able to interpret them and make sense of them remains important. And otherwise, I'm closing, and I will be here in case of questions. Thank you.